Assalamualaikum and good day everyone. My name is Muhammad FAIZ bin RUSLAM. My matrix number is B112410212. Today, our group will present our assignment for BELK 2383, Power System Technology. The title of our presentation is Per Unit System in Electrical Power System Analysis. This assignment is under our lecturer, IRTS Dr. Muhammad HATTA bin JOPRI. Our group members are Muhammad FAUZI bin Muhammad KAMAL, Wong and Muhammad FAIZ bin RUSLAM. In this presentation, we will explain how the per unit system is used to analyze a three-phase power network with different voltage level. First, the per unit system is commonly used in electrical power system analysis because it helps simplify calculation. In a real power system, the network may have different voltage level due to the use of transformers. If we calculate everything directly using volts, amperes, ohms, and NVA, the calculation can become more difficult and confusing. Therefore, the per unit system converts these electrical quantities into dimensionless value based on selected base value. This makes the analysis easier, clear, and more suitable for load flow and short circuit studies. For this PBL scenario, power utility suppliers and industrial facilities route a three-phase transmission network. The system consists of one synchronous generator, two transformers, one transmission line, and one industrial load. The arrangement of the system starts from generator G1, then transformer T1, followed by the transmission line, transformer T2, and finally the industrial load. The main objective of this project is to develop a complete per unit model of this system for future power system analysis. For the system data, this network starts with generator G1, which is rated at 50 MVA and 13.8 kV, with a reactance of J0.20 per unit. The power is then supplied to transformers T1, which is rated at 60 MVA. These transformers step up the voltage from 13.8 kV to 132 kV, and its reactance is J0.10 per unit. After that, the power flow through the transmission line, which operates at 132 kV with an impedance of J40 ohms. Next, transformer T2 is rated at 40 MVA and step down the voltage from 132 kV to 33 kV, with a reactance of J0.08 per unit. Finally, the industrial load is rated at 30 MVA and 33 kV, with a lagging power factor of 0.85. For this analysis, the common system base is selected as 100 MVA, and the base voltage at the generator site is 13.8 kV. This single line diagram shows the full arrangement of the power network. The power starts from generator J1 and is supplied to the industrial load through transformer T1, the transmission line, and transformer T2. Transformer T1 is used to step up the voltage from 13.8 kV to 132 kV for the transmission. After the power passes through the transmission line, transmission T2 step down the voltage from 132 kV to 33 kV before it reaches the industrial load. This diagram is important because it helps us clearly identify the voltage zone before continuing with the per unit calculation.
Hi, my name is Wong. Now I will talk about voltage zone identification. And here have three parts: Zone 1 generator side, Zone 2 transmission line, and Zone 3 load side. And for the voltage Zone 1 generator side, the base voltage for the bus 1 required is 13.8 kV given system base. And for the Zone 2 transmission line, the bus between bus 2 and bus 3 will use 13.8 kV, and 13.8 kV multiplied with 132 kV divided by 13.8 kV equals to 132 kilowatt. And for the zone 3 load side, as known as the last bus 4, will be using 33 kV, which is the calculation is 132 kilowatt multiplied with 33 kilowatt divided by 132 kilowatt. And now here shows the simulation setting by power word for zone 1, zone 2, and zone 3. And we can see in zone 1, the bus setting is 30.8 kilowatt. And for zone 2, bus 2, and bus 3, we use 132 kilowatt. And for zone 3, bus 4, we use 33 kilowatt. Then this is the part of the base quantity selection. We use the common base equivalent power as S base equal to 100 MVA, and the base voltage are selected according to the transformer voltage ratio, that is voltage base for 13.8 kilowatt, 132 kilowatt, and 33 kilowatt. And the base current and the base impedance also can be calculated by using I base equal to S base divided by square root 3 and divided by V base. And the Z base also can calculate it as V base power of 2 divided by S base. And now I will talk about per unit conversion formula, the main per unit calculation. So the formula is given as Z per unit new equal to Z per unit old multiplied with S base new divided by S base old and multiplied with power of 2 of V base O divided by V base new. And the given information is generator 1, given SO is 50 MVA, VO 30.8 kV, XO J 0.2 power unit, and the new system base is S base news 100 MVA, V base news 13.8 kilowatt. And for finding the new generator 1X, we put the formula inside. So the X power S, the ZPUO is J 0.2 and multiply with the 13.8 kilowatt divided by 13.8 kilowatt and power 2, and multiply with 100 MVA divided by 50 MVA, and we get the transformer, and we get the generator 1 per unit, which is J 0.4 power unit. And for the transformer new power unit, also same. We put the information. The ZPUO is 0.1, and we multiply with the V base O and V base new power of 2, which is 13.8 kilowatt, and then divide by 13.8 kilowatt, and then power 2, and multiply with the S base new divided by S base O, which is 100 MVA divided by 60 MVA, and we get the new transformer 1 J 0.1667 power unit. And now I will continue to transmission line and transformer 2. And for the transmission line, the formula will a little bit different from the other, which is the formula using is Z base equal to V base power 2 divided by S base. And then we can find it, the Z line power unit is equal to the Z actual divided by Z base. So we have it, the Z actual is equal to J40 ohm, and the V base is equal to 132 kilowatt, and the S base is equal to 100 MVA. And for the Z base of the 132, which equal to 132 power of 2 divided by 100, so we get the first answer, Z base 132 equal to 174.24 ohm. And then we finally can find the Z line power unit, which is J40 divided by 174.24, and we get the Z line per unit, J 0.2296 power unit. And for the transformer 2 is same as before. We use the S base O, V base O, and XO, S base new, and V base new, and we sub all the value to the formula, which is ST2 equal to J 0.08, and then multiply with 100 divided by 40, and multiply with 132 divided by 132 and power 2. And then we get the final answer for the transformer 2. ST2 is equal to J0.2 power unit. Next, I will talk about industrial load calculation and industrial load equivalent impedance calculation. For the industrial load calculation, the formula given is S load power unit is equal to S load actual divided by S load new. And the theta is equal to cos -1 power factor. And the power per unit equal to S load per unit cos theta, and Q per unit QPU is equal to S load per unit sin theta. And the given data is S load actual is 30 MVA, and the power factor is equal to 0.85 lagging. And we put the value into the formula first. S load PU is equal to 30 divided by 100, and we get the first 0.3 power unit. And the next, the theta is equal to cos -1, 0.85 equal to 31.79. And the power per unit equal to 0.3 multiplied with 0.85 equal to 0.255 power unit. And the Q power unit equal to 0.3 multiplied with sin 31.79 degree and equal to 0.1580 per unit. And lastly, we get the S load per unit 0.255 plus J 0.1580 per unit. And later that we can do the industrial load equivalent impedance calculation. And the formula given is Z load per unit equal to V per unit power of 2 divided by S load per unit. And the V per unit is 1.0 per unit, and the S load per unit is 0.255 minus J 0.1580 per unit. So the Z load per unit, we sub all the value inside that, and we get the final answer. Z load per unit 2.833 plus J 0.1756 per unit. And now after we calculate all the data, so we can get this diagram, equivalent unit reactance diagram. And for the component, generator G1, we got the per unit value J.0.4 per unit. And transformer T1, we get J0.1667 per unit. And for transmission line, we get J0.2296 per unit. Transformer T2, J0.2 per unit. And industrial load power J 0.255 plus J 0.158 per unit. And the industrial load impedance, we have 2.833 plus J 1.756 per unit. And the total series reactance, which is generator 1 G1 plus T1 plus transmission line and plus T2, and we have the final answer J 0.9963 per unit. And now this is the power word simulation result. And the system was modeled in power word simulation using 4 buses. The voltage level used were 13.8 kilowatt, 132 kilowatt, and 132 kilowatt, and with 33 kilowatt. This means bus 1, bus 2, bus 3, and bus 4. And the second, the load was set approximately as power equal to 25.5 megawatt, and the Q reactive power is equal to 15.8 megawatt. And the third one, the simulation confirms that the system arrangement follow the required network structure from the assignment. So in the circuit, we can see that the generator one is 25 megawatt and with a reactive power 23 megawatt. And the bus one, also known as the slack bus, with 13.8 kilowatt. And in the transformer one, we see that the result 25.46 megawatt, 22.74 mW, and 1428 ampere. And for the bus 2, we get the result 122.12 kilowatt. And for the transmission line, also known as the zone 2, 25.46 megawatt, 20.8 megawatt, and 149 ampere. And for the zone 3, the transformer 2 have a value 25.46 megawatt, 18.12 megawatt, and 597 ampere. And we go to the final, the load 25 watt, 25 megawatt, and 13 watt, which is near to the result.
Assalamualaikum warahmatullahi wabarakatuh. My name is FAUZI bin Muhammad Kamal. I want to talk about the engineering interpretation. I already stated 3 points. The first one is the generator reactant of J0.40 per unit is the largest component reactant in the system. This means the generator has a strong effect on the total system impedance and fault current limitation. So number two, the transmission line reactant of J0.2296 per unit affect voltage drop and power transfer along the 132 kV line. A highest line reactant can reduce voltage stability and limit power transfer capability. So the third point, the load value of 0.255 plus J 0.1580 per unit shows that the industrial load consumes both serial and reactive power. Since the power factor is lagging, the load behaves as an inductive load. Okay, for advantages of a unit system, I have listed 5 points. So number one, it simplifies calculation in multi-voltage network. Number two, it never large electric quantity into smaller dimensionless values. Number three is a low generator, transformer line, and load parameter to be compared on the common base, which is 100 MVA. It simplifies transformer modeling because if the turn into ratio conversion is reduced. The last one is it support load flow studies for analysis stability studies and digital simulation. That's all. Thank you. As a conclusion, the per unit model for this multi-voltage three-phase power network has been successfully developed. The system consists of three voltage zones, which is 13.8 kilovolt at the generator side, 132 kilovolt at the transmission line, and then 33 kilovolt at the load side. All equipment values were converted to a common base of 100 MVA. The final per unit reactant values are J0.40 per unit for generator, J0.1667 per unit for transformer T1, J0.2296 per unit for the transmission line, and then the last is J0.20 per unit for transmission T2. So for the overall of this project, the per unit system make the analysis more organized, easier to understand, suitable for the future studies such as load flow analysis and short circuit analysis. This show that the per unit method is an important tool in power system engineering. Thank you, that's all.